In this video, we're going to continue working with implicit differentiation, and we're going to use implicit differentiation to find the derivative of some functions that up to this point we have just been using, and those are for inverse trigonometric functions and logarithmic functions. And I'm going to give you a fourth part for implicit differentiation, where I'm going to give you some additional examples using these functions. We are going to start with the natural logarithm function, and that is ln x. Now, I know from this function that this is the inverse function to y equals e power x. This is going to be the starting point for me to deduce the derivative of ln x. How am I going to do it? I'm going to mix the process of finding the inverse function with derivation. So what I want to do in the next step is, starting from this expression, I am going to do the first step you do when you try to find the inverse function, and that is swapping the variables. So in this case is x is equal to e power y. Now that I have done this, I am going to differentiate on both sides. So derivative with respect to x of x should be equal to the derivative with respect to x of e power y. Now the derivative with respect to x of x is 1, and the derivative of e power y with respect to the x we have to do implicitly. So the derivative of that would be e to the power of y times the derivative of y because of chain rule. Now I have this expression and I can't really do anything else. So what I want to do is I want to go back 2 lines before and say, hey, I had defined e power y as x. So I'm going to take that and I'm going to substitute it right here, so that my expression becomes 1 equals x times y dash. And doing this, I get y dash is equal to 1 over x. Therefore, I can say that the derivative with respect to x of the function ln x is equal to 1 over x. Now let's consider the more general expression for the logarithm. Take log a of x as our next function. In this case, the exponential form of this expression is going to be x is equal to a power y. So similar to what we did for the logarithm, we are trying to do the inverse function of a power x, meaning we need to rewrite the expression that we know as a logarithm as an exponential, similar to how we did before. Now we want to differentiate on both sides, so derivative with respect to x of x is equal to derivative with respect to x of a power y, and we know the left hand side is equal to 1 and the right hand side is a power y times the natural logarithm of the base ln a, and then times the derivative of the exponent, which is y dash, following the chain rule. From here we instantly get that y dash is equal to 1 over a power y ln of a, and if we substitute with the expression that we had before, a power y would be x. So y dash is going to be 1 over x ln a. So for any logarithm of any base, the derivative d dx of log a of x is going to be 1 over x times ln a. Now let's do a similar process for inverse trigonometric functions. The first function we're going to consider is the inverse sine function. And similar to what we did with the logarithms, let's turn this function around as a regular sine. So in that case, I would have x is equal to the sine of y. Now we'll have to do the differentiation process implicitly on both sides of this expression. Again, we have derivative with respect to x of x on the left hand side, and on the right hand side we have the derivative with respect to x of sine of y. Derivative with respect to x of x is 1, and the derivative with respect to x of sine of y using chain rule is going to be cosine of y times the derivative of y, so y dash. Now I know that sine and cosine of y follow the Pythagorean trigonometric identity. Remember that sine squared of y plus cosine squared of y is going to be equal to 1 at all times, which means that cosine squared of y is equal to 1 minus sine squared of y. And going a little bit further, we defined sine of y as x, so we can substitute sine squared y with minus x squared. And then taking the square root for the cosine, and we're going to assume only the positive root, we are going to have cosine of y is equal to the square root of 1 minus x squared, which means that I can go back to the derivative and substitute this expression. Now my expression was 1 equals cosine of y times y dash, so I'm going to substitute here. 1 is equal to the square root of 1 minus x squared times y dash. So solving for y dash, I get y dash is equal to 1 over the square root of 1 minus x squared. So our final answer is the derivative with respect to x of the function sine minus 1 of x is going to be equal to 1 over the square root of 1 minus x squared. For the next derivative, let's consider the function y equals cosine minus 1 of x. And at this point, I would encourage you to try it by yourself first. Pause the video, try by yourself, and then look at the process that I'm going to show you to check if you did your process correctly or not. To start, we're going to do the same thing we did before. We're going to consider the equivalent expression but in the form of cosine. So that is going to be x equals cosine of y. At this point, we're going to differentiate implicitly. So the derivative with respect to x of x is equal to the derivative with respect to x of cosine of y. On the left side, we get 1. On the right side, we get minus sine of y times the derivative of y. We already know that cosine squared of y plus sine squared of y is equal to 1 because of the Pythagorean identity. And similar to what we had before, we are going to solve for sine of y. So sine of y is going to be 1 minus cosine squared of y, and we are taking the square root of this expression to get something to substitute for sine of y. Going back to the derivative, we get 1 is equal minus sine of y times y dash. We do the substitution. 1 is equal to minus the square root of 1 minus cosine squared of y times y dash. And we remember that x is defined as cosine of y. Therefore, we can substitute 1 equals minus the square root of 1 minus x squared in here times the derivative, and finally we solve for y dash as minus 1 over the square root of 1 minus x squared. Final answer is going to be derivative with respect to x of our function cosine minus 1 of x is equal to minus 1 over the square root of 1 minus x squared. For the final example, we are going to consider the function y equals tangent minus 1 of x, or the arctangent of x. Similar to the previous one, I would advise you to pause the video at this point, try it by yourselves, and then check whether you did your work correctly by looking at the process I'm going to show you next. To start, we're going to write the tangent version of the expression for the function, and that is going to be x is equal to tangent of y. Now we differentiate implicitly on both sides, so derivative with respect to x of x is equal to derivative with respect to x of tangent y, and to the left hand side we get 1, to the right hand side we get secant squared of y times y dash. At this point, we go to our bank of trigonometric identities, and we want to see what we can find for secant squared of y. So we're going to look at our Pythagorean identity. Sine squared of y plus cosine squared of y should be equal to 1. So dividing everything by cosine squared, we get tangent squared of y plus 1 equals to 1 over cosine squared of y, which happens to be secant squared of y. So from here we know that secant squared of y is equal to 1 plus tangent squared of y. Now going back to our derivative, 1 equals secant squared of y times y dash. I'm going to do the substitution of secant squared of y. I'm going to substitute for 1 plus tangent squared of y times y dash. So that means I need to put parentheses right there. And I can go back to the original, the first equation that I wrote, and that is x equals tangent of y. So we can substitute tangent of y with x, and this is 1 equals 1 plus x squared times y dash. Now solving for y dash, we get y dash is equal to 1 over 1 plus x squared. That means the final answer is going to be derivative with respect to x of tangent minus 1 of x is equal to 1 over 1 plus x squared.